Good morning. In this video, I plan to talk about the various molecular point groups and their notations. We start with molecules with no symmetry at all, then pass on to molecules with just one element of symmetry only, then molecules with more and more elements of symmetry, and finally molecules which are highly symmetric. I shall write down the list in the form of a table under 4 columns. First, number. Second, elements of symmetry. Third, notation. And fourth, example. The last column is made rather wide. We start with molecules with no symmetry at all. So elements of symmetry, none. Of course, other than identity. Their notation is C1. Most of the complex molecules are of this type. Some simple asymmetric molecules are carbon connected to 4 different groups like CH, Cl, Br, F, methane with an asymmetric carbon, then sulfur, bromo, chloride, etc. Then with just sigma alone, we call them CS group. These are planar molecules which have no symmetry other than the very molecular plane acting as a mirror plane. Examples are planar molecules, derivative of monohalo, derivative of naphthalene, 1 chloro, 1 bromo, 2 chloro, benzene, hypochlorous acid, etc. Then molecules with I alone, 3. I, center of symmetry alone. The notation is Ci group. For example, staggered, 1, 2 dibromo, 1, 2 dichloro, ethane. The Sawhorse projection can easily show the location of the single center of symmetry, chlorine, chlorine, hydrogen, hydrogen, bromine, bromine. This is the central point. Then a cyclobutane derivative like X, Y, Y, X. These are monovalent atoms or groups. The center of the square, there is the center of symmetry. Fourthly, molecules with Cn alone. The notation is Cn group. In this comes C2 group. Examples are hydrogen peroxide, Gauche, CS2Cl, CS2Cl, etc. The open book-like molecule hydrogen peroxide It has one hydrogen in one page like this, and another hydrogen flat on another page in this manner. And the C2 axis is bisecting the dihedral angle. Dihedral angle is around 111.5 degree. Then C3 molecule. C3. An example is PS thrice, triphenyl phosphine. It has a propeller-like look. The three benzene rings are not coplanar. It has C3 axis and nothing else. Then fifthly, improper axis alone, SN alone. Notation is SN group. The examples are rather rare. One example from F.A. Cotton, Chemical Applications of Group Theory, is of S4 group 1, 3, 5, 7 tetramethyl cyclo octa tetraene. This picture will be like this. If I start here 1, 2, 3, 4, 5, 6, 7. These are the methyl groups. It's an interesting example because it has no plane of symmetry or center of symmetry, and just because it has an S4 axis, it is not disymmetric. It is achiral. Another example is tetraphenyl methane. Now, with slightly more elements of symmetry, sixthly, Cn plus sigma H. You call them CNH group. C2H, example is trans 1,2 dihalo ethene. Molecule is planar. H, C, double bond C, H, X, X. This is the C2 axis, and this is sigma H. C2 multiplied by sigma H is center of symmetry. So its operations will be identity, C2, sigma H, and I. C3H, an example is H3BO3. It is a planar molecule. OH, 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 and this is the C3 axis, and this is sigma H. Seventhly, molecules with Cn plus N sigma V's. Its notation is CNV. A very large number of molecules belong to this category. C2V. For example, V-shaped molecules like H2O, H2S, Cl2O, OF2, S, Cl2, etc. Y-shaped like formaldehyde, carbonyl chloride, etc. T-shaped Cl F3, Br F3, etc. Seesaw shaped, like sulfur, not hexa, sulfur tetrahalide, sulfur tetrachloride, sulfur tetrafluoride. These have seesaw shape and belongs to C2V. Then of course molecules like CH2Cl2, then cis 1,2-dihaloethene. All these belong to C2V. Then C3V. Triangular pyramidal molecules like ammonia, nitrogen trihalides, phosphorus trihalides. Then monohalomethane, CS3X, etc. are of the C3V type. C4V. Square pyramidal molecules, iodine pentafluoride, bromine pentafluoride, xenon oxy tetrafluoride. The famous complex nitroprusside ion, Fe, Cn 5 times NO, 2 minus. The fourfold axis of the complex will be like this. Ion here, Cn, 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 Cn. This is NO. So this is the C4 axis. C5V. Here all examples are rare. Complex of formula Ni pentahapto C5H5 NO, having structure like this, a pentagon. The top there is nickel, above that there is nitric oxide. This is the C5 axis. The whole molecule looks like a pentagonal monopyramid. Now comes a set of 3 groups known as dihedral groups. These are characterized by a Cn axis and NC2 axis perpendicular to Cn. Dihedral groups. Characteristic feature is principal Cn axis and NC2 perpendicular to Cn. Dihedral groups. There are 3 types. DNH, which has Cn, NC2 plus sigma H. When sigma H combines with C2, which also lies in it, together it will give sigma V. So also it has got N sigma V's. Then because there is a Cn and a sigma H, their product, which is Sn, will also be present in the molecule, Sn. The list is very large. D2H, ethene, naphthalene, etc. D3H planar triangular boron trihalides, triangular bipyramidal phosphorus pentahalides, D3H, D4H square planar complex like tetrachloridoplatinate 2, a square planar molecule like xenon tetrafluoride, a square planar hydrocarbon like cyclobutane. These all belong to D4H, D5H, eclipsed ferrocene, C5, H5, twice Fe. The two cyclopentadienyl rings are eclipsed. This is the C5 axis, passes through the central ion, and C2 axis are here. If you observe it from the top, the eclipsed nature will look like two rings eclipsing each other. D6H, the sandwich compound, C6H6 twice Cr, dibenzene chromium. The benzenes are eclipsed to each other, chromium is in the middle. The sigma H passes through the chromium, here the sigma H passes through this ion in the case of ferrocene. As an example for D7H, you can quote tropylium cation. 1, 2, 3, 5, 6. 1, 2, 3, 4, 5, 6, 7. This is the C7 axis, which is also coaxial with S7 axis. As an example for D5H, you can quote the interhalogen compound iodine heptafluoride. It is a pentagonal bipyramidal molecule. You can classify that into D5H. Forgot to mention it earlier. Then D8H, eclipsed form of uranocene. Uranocene. We had mentioned this compound earlier, just to introduce a C8 axis of symmetry. One, two, three, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. This is cyclooctatetraenyl dianion, two negative charges, uranium or positive. It is sandwiched between these two eclipsed octagonal rings with a total 10 electrons. This will be aromatic. Then the DND group. In DND group, being dihedral, it is, I think the number now comes to 9. Ninth type, DND. Cn plus Nc2, no sigma H, but has N sigma Ds. its vertical planes are called dihedral planes. And Cn, when there are dihedral planes, this also will contain an S2n coaxial with Cn. Example of D2D, allene, one, allene is one example, then this 1, 3, 5, 7, cyclo, octa, tetraene. It's a tub-shaped molecule. There are no methyl groups, so it has planes of symmetry, C2 axis, etc. And an S4 axis. Example for D3D. The best example is chair form of cyclohexane. The chair form, this is how one writes the chair form. From this angle, if you observe it from this angle, these two triangles look as if staggered to each other. These two triangles look as if staggered to each other. These are of course connected. And this will be a C2 axis, this will be a C2 axis, and this also will be a C2 axis. The principal axis is this one, which is C3. So it has got C3 plus 3C2 plus 3 sigma D plus S6. Where is the sigma D? This is sigma D. This is one plane, here is another plane, and this is the third plane. 3 planes of symmetry, sigma D's. As an example for D4D, we always quote octa-atomic sulfur molecule, S8 molecule. It has a crown shape if you put sulfur atoms as circles, you will find that there are 4 categories of circles. 4 circles to the top, forming almost like a square, and 4 open circles to a lower level. Another, if you observe this sulfur molecule from the top, it will look like 4 sulfur atoms forming a square, and the other 4 sulfur atoms will be forming a square staggered to the first one. The sulfur atoms are mutually connected. This is connected in this manner. Being top, this is coming to the top. This will be C2 axis in this manner. C2 axis, and this is the C4 axis, and all these are planes. Such planes will be sigma D's. Coaxial with the C4 axis, there is an S8 axis. So it's a funny comment. If you say like this, S8 molecule has an S8 axis, D5D, D6D, etc. D5D, D6D, etc. There are many examples. Just now I remember one very important example which I forgot to mention earlier. As an example of D6H, I only mentioned C6H6 twice chromium, the eclipsed form. But there is a very simple molecule belonging to D6H, just overlooked its mention. It is our benzene. Benzene is the famous example for D6H. Now coming back to the DND type, D5D will be staggered form of ferrocene. Staggered. If you look it from the top, ferrocene, staggered will be looking like this. And these are the C2 axis. Axis like this. There is iron in the middle. Staggered. Ferrocene. Likewise, D6D you can say staggered sandwich compounds like dibenzene, chromium, staggered. As an example for D8D, again you can think of the staggered uranocene. Then lastly, the dihedral group is the one with axis of symmetry alone, without any planes. Cn plus Nc2. No planes of symmetry. No planes at all. Such a group is called Dn group. It has Cn plus Nc2. An example for D3 group. D3 group is metal complexes with ethane, 1,2-diamine, tris, ethylene, diamine, cobalt 3 plus or chromium 3 plus, etc. One way of writing its projection formula is like this. Put a circle for the metal, then the En groups are connected in this manner. So the picture will make you easily understand what the C3 is. C3 is along this line. I am holding it by this iron rod along this line, and C2 will be such lines. This will be C2 axis, C2, and this one will be C3. Now we come to the most symmetric molecules. We will discuss this under a special title, special groups. To special groups belong spherical molecules, like monoatomic molecules, helium, neon, argon. They are all spherical in shape. In fact, sphere is the most symmetric object. Then comes linear molecules with a sigma H and without sigma H. And there is a category of molecules whose shapes are related to regular polyhedra, like tetrahedron, octahedron, icosahedron, etc. The last category have many high order axes. We shall discuss these as a special video later. Now one more point I have to tell you. The notations for elements of symmetry, symmetry operations, the various point groups we have been using so far are called Schoenflies notations. S-C-H-O-E-N-F-L-I-E-S, Schoenflies notations. Symmetry aspects apply to crystals and the lattice-based crystal structures. In crystallography, we have got both point groups and space groups. The notations for symmetry elements and the symmetry groups in crystallography are somewhat different. Their notations are described as Hermann-Migne notations or simply crystallographic notations. We shall compare the Schoenflies and crystallographic symmetry notations in the form of a table. S-C-H-O-E-N-F-L-I-E-S, crystallographic symmetry notations and elements of symmetry. For the proper axis in Schoenflies, we have been using Cn, where n is an integer. There is no restriction for the n value. But here in crystallography, proper axes are simply called n. Its values can be 1, 2, 3, 4, and 6. Proper axes of order 5, 7, etc. are not seen in the discussion of crystallographic symmetries. In plane of symmetry, here it is sigma, here it is m. Center of symmetry, center, it is I in Schoenflies, it is 1 bar in crystallography. And the improper axis is Sn and its definition is Cn followed by sigma h. The very definition of improper axis is different in crystallography. It is denoted by n bar and it is actually Cn followed by I. It is a rotation inversion axis. In molecular symmetry, improper axis is a rotation reflection axis. In crystallography, it is a rotation inversion axis, and the values of improper axis are 1 bar, 2 bar, 3 bar, 4 bar, and 6 bar. These are the possible improper axes. Now comparing the Schoenflies and crystallographic symmetry notations, we have come across with a few identities like S4 is the same as 4 bar. Then 6 bar is the same as S3. 3 bar is the same as S6. These equivalents have been found between Schoenflies and crystallographic notations. With this particular video is being stopped.